Theorem 27, we're going to look at the first part here. It says every point in the perpendicular bisector of a line is equidistant from the ends of that line. So in essence what we're saying, if we have a point in this perpendicular bisector, if I said this is perpendicular to AB and that AC equals BC, and I had this point and I just labeled it P, if we have a point in the perpendicular bisector, it is equidistant from the ends of the line. So it would be the same distance from PA and PB. They would have the same distance, and we know distance is the distance of the straight line between the 2 points. The straight line that joins 2 points is the distance. So there we go. So we're just going to try to prove that P is equidistant from A and B. Here we go. We're given, again, line AB, or line segment AB. We're given that DC is the perpendicular bisector, and we are given the point inside that perpendicular bisector. And we're trying to prove P is equidistant to A and B. Number one, given. Number two, let's draw some auxiliary lines. We're going to draw AP and BP. Number two, reason 2 points, determine a straight line. Let's quickly draw those. Doesn't have to be perfect, just so that our eyes can see and it's easier to envision. Now we're going to state something about the angles down at the foot of that perpendicular. We're going to say, and I'm just going to label these angle 1 and angle 2. I'm going to state that angle 1 and angle 2 are right angles. Angle 1 and angle 2 are right angles. And that's the definition of perpendicular lines. Perpendicular lines form right angles. Number 4, let's state the obvious. PC is equal to PC because of identity. This line right here, equal to itself. Number 5, we have AC equal to BC. This is, let's just talk about this. AC, where is my laser? There we go. AC equal to BC. Well, that's just the definition of a segment bisector. We're told that DC is the perpendicular bisector. So those two segments would be equal to each other because the entire line segment is being cut into two equal parts. Definition of segment bisector. Number 6, I'm going to say that triangle PCA and triangle PCB are right triangles. Definition of right triangles. So these two triangles that are now formed, right triangles. Not rocket science. They both contain a right angle, makes them a right triangle. And now I can say that triangle PCA is congruent to triangle PCB. I'm going to give you guys a couple seconds to figure out why these are congruent to each other. We have a leg here and a leg here equal to each other. We obviously stated that they're both right triangles. And we have PC equal to PC. This is by leg. Number 8, we can state that AP is equal to BP. These two lines, AP equal to BP. Because of CP/CTE, corresponding part of congruent triangles are equal. Number 9, P is equidistant to points A and B. Number 9, definition of distance between 2 points. Theorem 27a. Let's quickly talk about Theorem 27b. It says that every point equidistant from the ends of a line lies in the perpendicular bisector of that line. So this is just the converse of the first part of the theorem. A, was stating that if there is a point inside the perpendicular bisector, then it is equidistant to the ends of the line. Now we're saying if we have a point that is equidistant to the ends of the line, then that point must lie in that perpendicular bisector of that line. So we're given line AB and a point. You can label it anything you want, such as P, saying that it's equidistant to the ends of the line. AP equals BP. Trying to prove that that point is in the perpendicular bisector. Number 1, given. Number 2, I'm going to state that we're going to draw DC through P perpendicular to AB. We can say 1, and my pencil is all of a sudden not working correctly, so let's quickly do that. 1 and only 1 perpendicular can be drawn to a line from a point outside the line. So if I were to draw this line through point P, there's only one line that can go through that point that is perpendicular to AB. And so I'm going to draw my auxiliary line real quick, DC, and we're saying that we're drawing that line perpendicular to AB. Number 3, I'm going to state that PC now is equal to PC. Oh, I need to move that down 1. PC equals PC, obviously because of identity. Number 4, angle ACP and angle BCP are right angles. Definition of perpendicular lines. Number 5, I'm going to state the triangles now are right triangles. Triangle ACP and triangle BCP are right triangles. Definition of right triangles. Number 6, we can state that those triangles are congruent to each other. My goodness, my mind is not working right now. Triangle ACP is congruent to triangle BCP. Again, let's take a look at why we can say that. Let's see what we've already stated. I've stated that this side is equal to that side. Stated that really these two angles are both right angles. So we can say that these two right triangles are congruent by hypotenuse, leg. Both of them have equal hypotenuses. Both of them have one equal leg equal to each other. And so we can say hypotenuse leg here. And number 7, AC equals BC. Oh, mamma mia. AC equals BC. These two lines equal each other. And so look at that. Just with that, we can now see that point equidistant from the ends of the line lies in the perpendicular bisector of that line. So AC equals BC because of CPCTE real quick. CPCTE. Number 8. The perpendicular bisector PC also bisects AB. Number 8, sorry. Definition of a bisector. And so obviously P is in that line, so P lies in the perpendicular bisector of AB.